Hi everyone, my name is Prince Salamofu. I'm 13 years old and I'm in 8th grade. And today we're continuing our periodic table lesson in part 2, and we're also going to dive a little bit more into atoms and ions. So let's get started. In the previous lesson, we talked about how APE stands for atomic number, protons, and electrons, and how they're almost always equal. But there are a few exceptions to that. For example, when an ion is formed. An ion is formed when an atom loses or gains an electron. This happens in an electron transfer, chemical reactions, energy changes, and more. In conclusion, ions are formed when there is a change to the electron state, which in turn causes there to be an imbalance within the atomic number, proton, and electron count. Now we're moving on to the atomic mass and the atomic number. Now that we've concluded that the electrons need not always be equal to the number of protons in the atomic number, how do we calculate the atomic number? If we look at titanium as an example, the electrons and the atomic number are both still equal because this is a neutral atom or element. But if there was an ion to be formed and the number of electrons was not equal to the atomic number or the number of protons, how would this be calculated? Well, to put it simply, the atomic number is just the number of protons within an atom or element. This is why all of the elements have various atomic numbers, because the protons vary from atom to atom or element to element. Now, when we're looking at the atomic mass is calculated by the sum of all the masses of the neutrons, electrons, and the protons. The mass of the neutrons and the protons is roughly 1 atomic mass unit, whereas the mass of an electron is 1,836th the mass of a proton or a neutron. When we take a look at our periodic table, we notice all these different groups that our periodic table elements are split up into, and we tend to wonder why they're split up into the groups that they're in. Well, the reason that they're split up into these groups is because elements in the certain groups that they're in tend to have similar chemical and physical properties. These properties can include valence electron configurations, reactivity patterns, and gradual variations on the physical model of an element or atom. When looking at a periodic table, we tend to notice some things that don't quite look right. For example, these 2 rows at the bottom that are supposedly supposed to fit in these 2 boxes, this random gap in the middle over here. But there are a lot of good reasons for why the table is set up like this, and one of the main reasons is to keep the order of the atomic numbers, as well as the groups and periods and valence electrons. An interesting fact about the atomic symbols is that they're not always derived from the words of the elements that we use. For example, iron doesn't have the letters F or E in it, so why is the atomic symbol for iron Fe? This is because it's actually derived from the Latin word for iron, which is ferrum. This is also similar to a couple other examples of elements like silver, gold, mercury, and so on. For example, gold isn't actually Au, and it's derived from the Latin word once again, urum or aurum. On this periodic table, when we click on an element to look at what it would look like on our diagram, this is nothing what it would look like on a real element. A real element would look something like this. It's actually amazing. If we look at it at a closer level, we can see that the electron ring isn't actually in a ring formation. At a subatomic level like this, it's a quantum electron field. And if you want something really scary to think about, this atom looks a lot like our Milky Way galaxy. Could you imagine if our galaxy, as vast as it is, was the equivalent of a single atom to a being that we could not possibly imagine? That's all for today, and I'll see you guys in the next lesson.